Let's start. I would like to briefly go through some activities of Laboratory of Microelectronics to tell you what is going on and what has been going on in the past. Thank you. As said already, LMFE, this stands for Laboratory for Microelectronics at Faculty of Electrical Engineering, started half a century before to be an elite laboratory dedicated to collaborate with industry to help to upgrade their products to the state of the art with a high added value and with a success on the market. We will, LMFE, will continue the collaboration with international and domestic industry. The future plan is to strengthen the ties with the neighboring countries. I cannot go into the achievements of LMFE because they are too numerous and it would be boring to just telling you what we did. We were good. The most outstanding are well known in the community of professionals active in the research and design of innovative basics. The aim of this talk is to focus to current status of development in LMFE and discuss the future. There are some publications around where we can find something if you want to read more about it. So there was a video at 50th anniversary of LMFE, and this is available on the website. The second possibility is the video of Archive of National TV Slovenia presenting some of our achievement when I received the PUH Award for Life Achievements for my contribution to Slovenia microelectronic science. There is also a large written text in my overview of history of Slovenian microelectronics, lately published by Slovenska Matica. I spent some time in Silicon Valley. Over 50 years ago, I was among pioneers in Silicon Valley, involved in the movement of designing and producing microelectronics chip. This was then a very hot topic. Microelectronics is nowadays among the highest priorities in EU. Even in Slovenia, some are dreaming about our Slovenian Silicon Valley, not knowing or not acknowledging the excellent achievement of LMFE in microelectronics. The mission of LMFE is to educate young professionals and mentoring excellent PhD candidates through their research work for science and industry in the field of microelectronics. We are internationally recognized. We have put small Slovenia on the prestigious place on the world map of microelectronic design and technology. We are the fathers of a method of mixed signal design on a single chip, and I am the leading author of the professional book Analog Digital ASIC Design by McGraw-Hill Company which presents the method how to include the digital and analog circuits on the same ASIC. This was at that time unimaginable because of the disturbances caused by large digital current spikes to sensitive analog circuits. I have given several hours lectures at Stanford University, and this was recorded by IEEE educational program. This is the flyer of our book, where I was the principal author, and it was, as you see, the first and the new. This is the book. It has been printed in more than 3,000 copies, which is for the book of these contents. This is a scientific group, is quite a good number. Also, my lectures at Stanford University were taped, and this tape is available, still available at IEEE Education Department. LMFE is active over half of a century, designing ASICs for Slovenian and international industry. During this time, we had authored and patented by several innovations. The most important one were the patents and scientific paper of magnetic systems on a single ASIC to analyze external magnetic field for its accurate position measurement. This is one example of this research and finally also product. This is the chip which shows around a circle around the ASIC with 64 magnetic sensors. These are special sensors. We are calling them micro-Hall elements because they are like pixels, and you can sense with this ASIC circular position with extremely accuracy. It's not on degrees, it is on seconds, angular seconds, not degrees. So it's very, very interesting chip, and it has been produced, this process has been produced in millions. For now, I know that currently there are 5 million already on the market. And the pixel, magnetic pixel, is micro-Hall element. Why micro? Because it's so small. Usually, the integrated Hall elements were one chip, big, several millimeters times several millimeters. Now we are working 24 micrometers times 24 micrometers. So it is really a pixel, small pixel. You can use it for different applications, not just sensing big external field, but to detect any thing which could be of interest. For instance, of interest is rotation, positioning, or speed, or whatever you can imagine. Yeah. Now I am talking about some results of LMFE, which are, let's say, unique because they are first things in the completely society of ASIC designers. We have designed a telephone chip, which was used for standard telephones. Standard telephones, electronic, had a lot of functional, made with discrete components, transistors, and so on. And at that time, the CMOS technology was considered only to be a digital technology. But the telephone needs to have some very complex functions. I don't know if you remember from school times what is the fork, telephone fork. Maybe you don't. But we were able to do it in CMOS technology, first in the world. It is worth to mention also that in the Silicon Valley, we were working with company, American Microsystem Corporation, AMI, we call it, AMI. And LMFE, we had a joint development team there. I was the head of this joint development team, and we decided to make something new together. And the new thing was to make an integrated microcomputer, not microprocessor, microcomputer, meaning that all functions should be integrated, all peripheral units which you needed if you want to make a computer with only microprocessor. A lot of other electronics should be here. We integrated everything. Clock time, asynchronous adapter, asynchronous digital adapter, and so on. Everything is in this. And we had also, at that time, unfortunately not any longer, the company Microelectronics, which also produced this. And it was known as EMZ 1001. We were able, which is not known, we were able to produce silicon chip, completely fab, micro fab, I would call it, or mini fab. So we were able to produce this. And we also developed the production process. Well, this is also not known a lot. This was in former Yugoslavia, and we collaborated with the defense program of Yugoslav army, and they asked us if we can do something for their rocket, Earth-to-air rocket. And we did it. So it was 4 chip having all the digital electronics to guide the rocket, sensor electronics to sense the, for instance, airplane you want to hit it, and so on. So we did it, this, and this is part of the rocket which was built, and there are our chips. This is our chip, and this is our chip. And due to those two chips, actually there were 4 chips, but we see only 2. Due to our chips, the space occupied in the electronics which were done on the discrete components was half, which means that the weights of the rocket went down, or the space for explosive has doubled due to that thing. Oh, let me go back again. This is not known. Our sensors were so good that sense also the stealth airplane, stealth bomber. And I don't know if everybody knows that we grounded, not we, but Yugoslav army grounded a stealth bomber near Belgrade using this sensor. So it was invisible, but not invisible for our sensors. Okay, so this I already talked about. We did also this telephone ASIC, first time on the world. And this is another very interesting chip. This chip is detector for X-rays. The way how it works is that this has 64 inputs, and the line you want to measure the baggage or the details there is made out of 1024 sensors. So this was so economically interesting that this chip was built in all X-ray sensors at the airports, in all. You remember this at the airport. This is X-ray checkpoint at the airport, for instance. And all of a sudden, the consumption of those sensors increased more than 100 times. Why? Because in the United States decided to check the school bags of the children coming. So this was a huge number of elementary schools, so the chip became a very economical, effective. There is another ASIC which is quite interesting because it is used to sense the surface of an object, touch probe. You have to be able to measure the roughness or the anomalies on the surface of the object, and it has to be very, very sensitive. We are looking about few microns roughness. This is another system we designed for Volvo. Volvo decided that their airbags are dangerous for weak person or children, and when the crash happened, the guy who would be protected by the airbag was weak, and if the airbag hit him, it was injured. There were also some deaths of children because the airbag was too strong for them to survive. And they decided to incorporate our chip and our system to help to measure the speed and the position of the seat belt during crash. I just want to tell you that the future of microelectronics is bright, because as you have seen, we are not behind. We are able also to provide chip process. We have processing, not only designing. We collaborate also with our photonics laboratory, and we think that the collaboration can be fruitful, because the photonic circuits are of course fast and effective, but for more complex processing they are not so good. So you would like to do this with some algorithms, with some digital processing and so on. I would like to tell you also some other story, which is that we are working also on terahertz sensors, and we have designed and patented a new best room temperature operating terahertz sensor with a microbolometer. This bolometer has been used by Professor Gintaras Valušis from Vilnius Institute for Physics, and he wants just our sensors. There are no terahertz sensors they could buy with this sensitivity and with this accuracy. Terahertz waves are used also for medical diagnosis. Just the group of Professor Gintaras Valušis proved that humor cancer tissue is detectable, very reliable detectable by terahertz, which is a promise for easier and less painful characterization to find or to diagnose a malign tumor. So I would like to conclude by expressing my deep gratitude to all of my co-workers in LMFE and the Faculty of Electrical Engineering for their understanding and moral support when we were facing crisis and fighting for survival. Thank you.
thank you, Professor Trontelj, for sharing with us these great achievements of your lab. So it seems us that you have a magic stick for chips. So many numerous chips and for different applications. So now it's time for questions and comments. Any question? So maybe I can ask you,
Yes.
how do you see the future of microelectronics in Slovenia, in short? So we learned about the subsidies from the government and so on. So what is your opinion and your view on that?
Well, my view is that, of course, we want to be commercially effective. But the small group, this is not fab, very big fab. This is a small fab. Maybe 20 people is working on that, not more. And we cannot sell the products at the cost which would be from the big fab. It's impossible. So the only help would be to understand that they are able to have also a small fab, but not working. We cannot sell one chip compared to the price compared to the big fab. It is impossible. So government should understand that we can do almost everything, but not for nothing. It's impossible.